you and I have spoken before the episode, before this conversation, about your friendship with Lee Cronin. And what I wanted to ask is why he describes the field as pre-paradigmatic. And I think that maybe this will connect to what we were discussing about like, a narrative being kind of displaced by experiment and why experiment is so vital. But maybe first, and I'm sorry I'm throwing so much at you,
Yeah, no, that's all right.
I'm just curious what it is that you two are working on together and how it is that you know each other.
Yeah, so I think the question of like what is a paradigm is an interesting one in science. Obviously, that comes from Kuhn, um, but I think people don't think enough about science as a social system, especially practicing scientists. So maybe this gets more into the philosophical discussion that we're having. But science itself is a cultural system. It has certain cultural norms, and people operate under certain kinds of understanding of the world. And so, a lot of the places where we don't have answers in science are really because there's not a paradigmatic framework that people feel is an adequate explanation for those sets of phenomena. So, when I was talking about the origin of life before and saying it's really outside of chemistry, it's outside of biology, it's outside of physics, another way of phrasing that is to say these fields have paradigms of like how they think the world works, and the original life is somehow fallen between the gaps of all of those paradigms. And so, just as an example, biologists have evolutionary theory, which works exceptionally well once you have a cellular architecture and a genome, but it doesn't really help you with pregenomic evolution. And in physics, we do great with equations of motion and initial conditions. And once you have an initial condition in dynamical law, you can describe the trajectory, planets or whatever it is that you're doing, or even quantum systems, those kind of things. But in living systems, they seem quite open ended. So the origin of life, in some sense, is kind of the beginning of an open-ended cascade of novel forms that aren't really predictable from an initial condition. So like there's all of these things in chemistry, really they focus on like a single reaction, not like these messy chemical systems like that are, unconstrained chemical messes. And how do you fingerprint molecules, if you don't already know their prior identity? It's not really like what chemists are doing. Chemists are interested in organic synthesis and trying to synthesize this particular molecule in high yield, not do this process of the original life. So there's this issue with these paradigms. And so it's interesting being an origin of life scientist because no one's trained in origins of life, right? Like you could do a PhD working on origins of life, but you're not really trained in origin of life because it's not an established science. It's a question that people have that we don't have an answer to. And so when you start working in that field, it's really fun, because you meet people that have really really different perspectives than you because their training is so different. So I came from a cosmology group. My training is in theoretical physics. Like my coursework was in standard theoretical physics, cosmology, quantum field theory, all that stuff. But I'm working on this problem, like thinking that there's some kind of fundamental principles. And as I mentioned, most of the people in the field are trying to synthesize particular chemical building blocks. But then I meet Lee, and Lee, for people who know him, he's quite an interesting person, very passionate about his work, but also asking really hard questions and asking them in very unconventional ways. So he was like the first person I met that was a chemist working on origins of life, where I actually thought there was an experimental program that I could get excited about and like was actually trying to tackle some of the problems that I'm interested in. And the way that Lee was approaching it, which I found incredibly inspiring, was not to actually try to engineer under some kind of very specific conditions the molecules that we know in life. So he wasn't trying to do this post selection, where he's saying life on Earth evolved this. Let me just find the root to that, and then I'll claim I solved the origin of life. Um, he was saying, let me start with chemistry. Chemistry is incredibly messy. Like, what kind of constraints in a chemical system lead to, constraining this sort of combinatorial mess? So I start to see the emergence of an evolutionary system. And even better than that, he was asking, like, how could I measure that? And at the time I was working, I still work a lot with Paul Davies, who's my postdoc mentor. But Paul and I have been talking a lot about this idea of a life meter. Like if you were going to measure life, like you want to say the origin of life is a physical transition, there should be some kind of measurement, almost like a phase transition, like you can measure, a state change in a physical system. We were thinking like, what if there was such a thing for life? And Lee was actually in the lab trying to like physically do this. So that's how I started working with Lee, was just I like some of the ideas I was thinking about with the nature of information and causation sounded a lot like how he was thinking about the nature of life. I think at the time we were calling it like a non-trivial trajectory through state space, whatever that means. But that came from me because I was on my side, like I think, as I said, Lee and I were thinking about similar things. But on my side, I have been working with Paul on this idea of state dependent dynamical laws. Um, so this is like a whole side tangent. But the idea, like in physics, the way that we write all of the equations in physics, all of the laws of physics are written as an initial condition in a fixed dynamical law. But I mentioned this problem of this open-ended evolution in biology, and also there's a lot of interest in the fact that biological systems seem self-referential, which in some sense implies that they can change the rules of how they behave as they go. The classic example is like epigenetic modifications of the genome, which can be inherited and change the dynamics of how the genomic information is read out. But there's lots of examples of this kind of feedback, where the dynamics of biological systems somehow depend on the history. And so Paul and I were playing around with this idea, in cellular automata models and these kind of things, with asking questions about if the laws of physics weren't fixed, but they changed as a function of the state of the system, like what kind of systems would those look like? And so I was really thinking about how life basically constructs itself. Um, and how would you build a constructive process as a trajectory in a dynamical system? It turns out like I don't think that's exactly the right way of the way I just said it. I think is still the right way of thinking about state dependent laws. I don't think work for lots of reasons. One of them being you can always just write it the dynamics as a fixed law at like sort of another sort of coarse grain scale. But anyway, that was what I was thinking about when I met Lee, and Lee was thinking about this idea of non-trivial trajectories, which is kind of a similar sort of constructive process, but really thinking about it in an embodiment in chemical systems. Like these molecules are producing things that you wouldn't expect, and he has experiments that are actually not reproducible. So one of the things that he always says is he's looking for reproducible irreproducibility. So you might get to a similar level of complexity, but you won't see the same molecules again because the trajectories are there's so many of them of the way the molecules could actually react and form more complex structures that you're building into the space of more complex molecules, and seeing the same sequence of events twice is almost impossible because the space of the combinatorics is so large. But you might get to like the same level of complexity or something. So that's what he was thinking about. And then I got really sold on collaborating with him and like thinking more deeply because of the way that he was thinking about embedding it in measurement, which was the initial development of assembly theory and this idea that you could measure the complexity of chemical systems by the minimum number of steps to produce a molecule, recursive number of steps. So we can get into that if you want, but the basic idea being there's some kind of shortest possible way of getting to a molecule. And if you can measure that, then you can kind of bound how complex the system has gotten. And there's some conjecture that we have that the origin of life is the transition above a certain threshold in complexity. There's like an abiotic upper bound of how complex a non-living system can be. And life is the mechanism that crosses that via selection and evolution. Information processing are all the words that people like to use as buzzwords to describe life. So to circle back, so that's why I started working with Lee. And I think we both have kind of a similar spirit about this nature of paradigms, to get back to your original question, that both of us were much more interested in actually solving the origin of life than working within the existing paradigms. So a lot of times what you find is like when you're trained as a scientist, you're trained a certain way to think and you want to kind of contribute within that way of thinking. And we're not really taught to just like kind of forget the things we learned and just look at the phenomena that we're trying to study and ask from first principles, how would I solve it? And I had a really deep, probably because of my training in theoretical physics, but also my personality, I had a really deep conviction that none of the current ways that we were talking about it were going to solve it. And we just need to start from scratch. And Lee had a similar conviction. And so, in some sense, when you're doing that kind of science, you know you're not working within a paradigm. And then the question it becomes like, what paradigm would emerge if this problem was solved? And I think about this a lot because I think, if in 20 or 30 years people are saying the origin of life is solved, what kind of new explanation does humanity have for the way that reality works? And I use this to guide the way that I think about the problem. Like, what things should the origin of life solve? What else should it explain? What other areas of science should it impact? What kind of questions can we ask? So that gets back to your point about Mike Levin. I very much agree with this perspective that science, like, in some ways, when you're asking a question like, what is life? People have definitions for life, and then they'll work on that question within that definition. But if you have an entirely new way of framing it and it becomes a quantitative tool, and maybe a new theoretical framework, that opens up all kinds of ways of asking questions that we didn't have before. And I still believe this, but like, I used to say this a lot more than I have been lately. But I think one of the things that I've always pushed, try to get new ideas into my field, is exactly for this reason. Because even if I fail, like, maybe if the program that we're working on doesn't end up being the ultimate explanation for the origin of life, like, I think it's the most promising approach we have right now. I'm really excited about it, but it could fail. And if it does fail, I at least have the hope that, like, our effort and all of the work that we're doing would really inspire a lot of other people to think differently. Because otherwise, if we don't do that, the field is just totally stagnated and we're not going to solve the problem.